Good afternoon. Very happy to be here. My name is Malcolm Humphrey, and I'm Vice President and General Manager of our core compute DRAM business inside of Compute Networking Business Unit. And I'm actually joined in this session by Roger Peene, who's our Vice President and General Manager of our Data Center Storage business inside of our Storage Business Unit. And we'll be teaming up for this next section, which is entitled Roadmap for Memory and Storage Innovation. Public service message. So just a reminder that this session is still covered by the safe harbor comments we made from the earlier session. I won't go into the details of that, but you guys know it well by now. I guess where I'd like to start is to note how valuable data is and that customers need to be able to extract that value. I think both Raj and Ryan talked about some of that. We're certainly at a time of increasing performance requirements, and that heterogeneous data center and those workloads that Ryan mentioned are at a scale now that encourages, if not commands, the optimization of the hardware architecture, not just the software. So, Ryan talked about this hierarchy. I like to think about it as we need to get the data to both live and then actually work at the right level of both latency, capacity, bandwidth, where it's optimal in place for each type of the workload that it's destined for. So whether it's that future CXL attached memory that Ryan spoke about in the preceding session, or high bandwidth memory in the form of HBM, right? That near memory that we talked about, really wide, really close to the SoC or processor, or the imminent generational changeover of the traditional memory bus, that bandwidth memory layer that Ryan talked about, to the next generation of DDR. Micron is committed to working with our customers and the entire ecosystem to drive the development of things like the necessary standards, to innovate across a memory and storage portfolio, and to address each one of those tiers of both memory and storage, which Roger will talk about, in a thoughtful and compelling way. Okay, so the first thing I want to talk about are the aspects of kind of technical collaboration that this sea change requires. And the first is the area of open standards. We talked a little bit about CXL already. CXL is one form of an open standard. Anyone can join the CXL consortium. And effectively, as Ryan pointed out, it includes every major company in our industry. And certainly Micron is excited to deeply engage with other industry leaders there, charting the path to a CXL-enabled future. But we also have the tried and true JEDEC. And Micron has long been a participant in JEDEC, has had leadership roles throughout the various generations, DDR4, now DDR5, GDDR6, recent great examples of Micron collaborating and in some cases leading within JEDEC. And of course, JEDEC, along with Micron inside of JEDEC, is even doing early work on the potential needs and potential approaches for next generation standards like GDDR7 and DDR6. We all know at Micron what it takes to align across the industry to get things done for the betterment of not only Micron, but the entire industry. But the technical collaboration need also goes further than just the standards and consortia, right? It includes what I would call bilateral support and bring up. That's working directly with customers, but also with partners and enablers. And recently, we created a program called Technology Enablement Program, and for DDR5 specifically. This was the first time we formalized this support infrastructure to bring together all the information that a customer or partner would need in the form of traditional things like data sheets, but also things like models, behavioral, signal integrity, and also thermal models. Part number decoders, technical support and training, and bring together everybody in a sense of community so that they can actually connect. And we've worked with partners developing all these standards-based solutions from DDR4 to DDR5, from G5 to G6, even sometimes outside standards when we've had a particular bilateral collaboration to bring a new technology in advance of the standard works, like our recent example of GDDR6X, where we took the innovative approach to multi-level signaling, in this case PAM4, to enable very high-speed I/O on what is already a very high-speed graphics DRAM. Ryan talked about HBM2E, high bandwidth memory. And also in the storage area, GPU direct storage. In that case, Micron partnered with a leading edge performance system enabler for the testing and implementation of system GPU direct storage, which reduced the latency and increased the throughput when accessing large blocks of storage. So Micron knows what kind of collaboration needs to be done to get things done, and our role, both in the standards-based and in some cases proprietary-based approaches to things, is to enable the entire ecosystem, and we feel like we've really been leading the way there. I want to talk about the top several layers of this hierarchy, and Ryan covered near memory, right, where Micron previewed our solution last September in terms of HBM and our approach to bring the highest possible bandwidth close in time, that latency you talked about, but also close in space because those related, hence the proximity to that SoC for applications where the bandwidth demands are the highest. And so for HBM, bandwidth density and low power are key. Talked about bandwidth memory, the traditional memory bus, and DDR5 is taking a leap forward, delivering both density and bandwidth optimized for mainstream applications. Bandwidth memory, this DDR bus, is still the dominant memory tier in terms of volume and value to our customers. We do not see that going away anytime soon, and it's really complemented by these other areas. And then, of course, the capacity memory, the CXL memory that Ryan spoke about, really exciting, soon to be here, but not quite here yet. So what I wanted to do maybe is take just a little deeper dive and focus on what the server industry in particular has been waiting for several years now, which is the advent of DDR5 memory, that change in the bandwidth memory structure. Okay, not to throw too busy a chart at you, but I'll start with asking the question, what's the problem with DDR4? And Ryan hinted at this. DDR4 has certainly been a great workhorse for the industry over time for a number of years, but in short, it's run out of gas because those core counts, that core count growth that Ryan talked about, continuing to grow at that 20+% compound annual growth rate, and we've come to expect, as both consumers and technologists, to enable that year-over-year performance improvement in our systems. That is driving the memory bandwidth per core to either be stalled out or in danger of actually shrinking, right? Because even as you add memory in the form of more channels or add speed, which also increases the bandwidth, we're kind of at the limits where you can do that with DDR4, right? So we're at 3200 speed. The leading CPUs have 8 different channels. We're as far as we can go, and looking forward, that memory bandwidth per core, which is that blue kind of flat line towards the bottom, is in danger of going down. And really that's what DDR5 starts to address. And you can see that in the table on the right. You can see the bandwidth per core, the core count going across the top, and the various speeds and standards going up the left-hand side. So in order to keep bandwidth per core flat or slightly up, you have to traverse that table from bottom left to top right. And that requires both the speed going up, but also some architectural changes, which I kind of want to talk a little bit about. So this is an easy one because everything on here is 2x. The initial, or one of the data rates, actually not the initial, one of the data rates of DDR5 in the not too distant future is 6400. So that's 2x the current data rate of DDR4. The burst length is 16. The burst length of DDR4 is 8. What does the burst length allow you to do? Well, burst length of 16 allows you to download the full 64-byte cache line for a CPU in one burst. And that takes multiple bursts with DDR4. So you get an efficiency gain there. Bank groups, 8. DDR4 is limited to 4. That effectively gives you an additional rank in a single DIMM. And then the total banks grow by 2. But the other interesting thing is if you just look at the data bus, right? There's these 2 independent channels, and they're 40 bits. But if you correct for ECC, they're 32-bit buses, 32-bit data buses each, right? Totaling 64 bits. DDR4 has one 64-bit bus, so you say, okay, what's the great benefit? You still got 64 bits. These are independent channels now. And so you get an efficiency gain by being able to operate them independently. And it's unclear, how big of a gain you would get for any of these things, right? The burst length, the bank groups, the data bus having 2 channels. So you can model that though, and that's what I wanted to show you next. So if you make some real world assumptions about what kind of accesses you're going to make, what's the system configuration, etc., and you hypothetically limit DDR5 to the DDR4 top rate, 3200, you can see like for like at the same transfer speed how much more impressive and how much more performance there is in a DDR5 system just from those architectural changes, right? Before we even add the increase in data rates, which DDR5 does enable. And so in our particular example, and I can share if anyone's interested, the specific assumptions we've made here, we believe they're middle of the road and they're certainly not best case. But in this particular model, the simulation that was conducted, we saw a 36% increase in just the architectural changes between DDR5 over DDR4. When you add to that just the very first stepping of DDR5 data rates, which is the 4800 data rate, and combine that with that architectural gain, the overall performance bandwidth gain goes to 87% in the same simulation. So right away, you have nearly a doubling of the performance as far as memory is concerned in a system by moving from final generation DDR4 based system to very first generation DDR5 based system. And so this is one of the reasons why, while we're very excited about CXL and HBM and all those other things, there's some great stuff happening even within the traditional JEDEC world that is leading to performance gains in our industry that are sorely needed and expected by our end customers.
Malcolm, I have a question. So you're talking about doubling the performance of RAM, so local RAM, but then you have CXL. I mean, it's not as fast. I mean, we are talking about probably an order of magnitude of difference for accessing RAM memory in this case. Okay, so isn't it the difference too large then when we talk about accessing local RAM and an expansion RAM to make it viable for most applications?
Are you talking the difference between accessing, for example, a DDR5 on the DIMM versus CXL attached to DDR5?
Yeah.
Yeah, I mean, Ryan talked about
you are moving, from the memory bus to the PCI. I mean, even if we will have a next generation PCI, the difference will be massive.
Yeah, Ryan talked about that a little bit, and I'll ask him to comment as well. But this is where I was saying there is a latency difference. It's not. We believe it's not as big as for example some latencies of storage class memory, right? So some of that is mitigated, but when you go back to the workload specific items, there's going to be different trade-offs, and certain items that need that expansion will allow for that that increased latency that CXL may bring. Brian, would you add anything more to that?
Yeah, I would add, it's about the hierarchy. It's about, stepping into new, tiers within that memory space. And when you do that, there's an associated economic benefit that needs to be traded off with, perhaps a little bit longer latency associated with accessing that particular, tier of
yeah, but we don't have any number to share yet. I mean, so that by moving data through this PCI, because when we talk about storage class memory, we can have storage class memory in the memory bus, okay? And there are a lot of techniques now to mitigate the latency using some of the memory, the RAM to cache or whatever they do to do this kind of things, and on the other side it's pure latency. You don't have any mitigation because you don't have control on a device that is external to the compute node. So I would like to see something that shows, what is going to happen. I mean, if it's 10 times the latency, it's a lot. I mean, I understand the benefit of having 10 times the latency is still good for some application, but for other application, it's totally useless.
Yeah, and of course, CXL sits between the DRAM and the storage class memory in that hierarchy. So you're going to get better performance out than the SCM. Our simulations are suggesting that despite that latency delta that you see in standard memory versus the CXL memory, by and large, the workloads actually behave reasonably well, given that despite that latency delta. When it comes to looking at a sort of baseline system versus a system equipped with CXL. And again, this is emulation.
Yeah. I mean, I don't like to play, the devil's advocate here, but actually, if I put DDR5, which is really, really expensive, on a CXL, I mean, it's very expensive. I'm expanding the memory of the node, but it's expensive. While with storage class memory, I get something that is less expensive than memory. I mean, right. So there are trade-offs on both approaches here. I mean, as far as I can see.
If I may, Ryan.
Yeah, go ahead.
I think, Enrico, you hit the point of what the hierarchy is. What is the gradient in the hierarchy is both latency performance and cost. Right? Two levels of the hierarchy will converge if they provide similar performance and similar cost. We see the CXL attached memory technologies sitting at a much lower latency than storage class memory, right? The second thing is, if you go back to how CPU caches have been designed, right? There is the last level cache is slower than the immediate level to the left of it, is designing how much capacity you need at what point in the memory hierarchy based on the performance. So if the media technology we're innovating in can move the latency lower, right, then the value of that goes up relative to storage class memory. And you will see it being used for memory semantic driven workloads rather than what people do today with storage class memory is have to write essentially software to translate from a block oriented transfer to memory semantics, which is usually cache line driven, or it's some level of byte line driven, and then support automatic paging in the system. So that's what we are looking at that's why this isn't just hey, there's a bus and you attach known memory to it. You have to innovate in the controller, you have to innovate in the memory to actually optimize for at what point in that latency and cost hierarchy you sit.
One of the most exciting things about CXL is while it's standardized from the interface, it allows innovation behind the controller. So those are some things we're looking at. I'm going to ask Roger to talk a little bit about, continue this hierarchy discussion and talk a little bit about the layers of storage. So Roger, over to you.
All right, thank you, Mal. Hi, everyone. My name is Roger Peene, and I'm the Vice President and General Manager of Micron's Data Center Storage Group, focusing on SSDs. So I'm here to talk about the storage segment of the hierarchy, and specifically the fast storage and the capacity storage tiers. With tens of zettabytes being created this year, applications are continuously requiring both faster storage with lower latencies, as well as ever increasing capacities in the most cost-efficient manner. And in the fast storage segment, we've seen a migration from the SATA Enterprise SSD, which came to market over a decade ago, to evolve to PCIe, and specifically the NVMe protocol interface on PCIe Gen 3. And the industry is now making a transition right now to PCIe Gen 4. And we're getting ready to migrate further to PCIe Gen 5 within the next 2 years or so. And so through this evolution, we've seen SSDs significantly increase their bandwidth and IOPS capability. Specifically, from SATA SSD to PCIe Gen 5, there's been an over 20x improvement in bandwidth from about 550 megabytes a second in the SATA SSD to growing to greater than 11, 12 gigabytes a second on the PCIe Gen 5 interface. And Micron has a broad portfolio of SSDs, and so we are the #1 shipper of enterprise SATA class SSDs in the market today. And we do that because we want to continue to support the very long tail in traditional enterprise. But it's very clear the market is moving to NVMe, and we also have products to support the latest standards with the latest performance capabilities. Now, the capacity storage tier in our hierarchy is a segment that was really defined as HDD storage, and I would call this a new emerging segment. Historically, this would have been the performance hard drive with 15K, short stroked hard drives, which were replaced by flash, and then 10K hard drives. And now the market's going through a transition to dual actuator hard drives. And we believe that it will eventually migrate to QLC-based flash PCIe SSDs with very, very large capacities. Now, in that traditional enterprise market, we actually offer QLC-based SSDs on the SATA interface, such that you could take advantage of the legacy infrastructure and you could pull out a 10K RPM hard drive and plug in a QLC-based SATA SSD and immediately realize significant benefits. But for larger deployments, I'll spend a few minutes later in the presentation articulating how QLC technology is going to solve some real IOP per terabyte challenges that modern data centers are faced with today. There's a ton of innovation occurring right now in the storage segment, including technologies at the SSD level of standards such as the Open Compute Project, security features we talked about, things like zone namespaces for SSDs. But the one trend that is a theme of this entire presentation is the significant focus on disaggregation model, including NVMe over Fabric. Now, NVMe over Fabric is just extending the NVMe commands over Fabric so that Fabric attached storage has better latency, better access to enable a disaggregated model, and you could build out a larger capacity of a storage pool with more flexibility. Now, in this current hyper-converged data center model, cloud providers would develop servers with fixed ratios of compute, memory, and storage. Then they built a lot of platforms that are run by many different applications. Now they get more scale by deploying more servers and more systems for scale out. But each of the applications use different amounts of utilization rates of the storage pool. Some are low, some are medium, and some are high. And the storage that doesn't get utilized is trapped by that compute node, and it can't be used by other applications. So it's essentially dark storage. This is no different than, let's say, in the networking realm of dark fabric where nobody is using it. It's a very inefficient use of storage. And so, in some regards, it's the same thing that's happening with memory. And Ryan was talking about CXL coming that will address the same issue in the memory space. Now, hyperconverged architecture started 20 years ago, but we're seeing a transition back to the shared model to get to the most efficient use model to right size for the task and the applications. Okay. Next slide. So to me, disaggregation, it's about pulling things apart and then how to put them back together when you need to spin up an application. Now, this shared model is nothing new. It was done with hard drives years and years ago. But when SSDs became available, they were direct attached to the compute node for the lowest possible latency. But with technologies like NVMe over Fabric and networking improvements, we can now get to much better latencies across that network. So we are adding several milliseconds, but it's on top of an SSD that has about 50 microseconds of latency. So the overhead is rather small by comparison. So, we were talking about this on CXL. It's not the most efficient model, but the benefits you get from that pooled storage economically definitely makes up for the lost latency through the network. So this configuration is becoming a lot more attractive. In the Amazon model, users, at some point would complain that you had to purchase services with a fixed ratio of compute and storage. Now, what you can do is you can configure the storage essentially on the fly. So if you're running a data center and offering infrastructure as a service, you can allocate dynamically the different ratios and optimize hardware for the application. So essentially, storage becomes a pay-as-you-grow model. So if we looked at this and we looked at kind of the data center fabric that we're talking about, you would have multiple servers, which is represented across the top of the slide, each with a CPU and networking card. And most data centers, are using an Ethernet network within the rack. And there's really two approaches that we can use here. One on the left-hand side is with PCI switching in a JBOF mode, or just a bunch of flash, and with a smart NIC or a DPU, a data processing unit, you can then have a PCI switch with a rack of NVMe SSDs on a PCIe backplane. The other approach is an EBOF, or an Ethernet bunch of flash with Ethernet switching. You would basically, from the NIC on the host down to an SSD, which has a direct Ethernet connection, and then directly access the storage. Now, the advantages to the EBOF implementation is it's a bit more cost optimized. The advantages to the JBOF is you're using a standard PCI SSD, but with that smart NIC, the DPU, and the switch, you can actually inject more storage services further in the stack. So you can run things like compression, erasure coding, or more advanced functionality. Now, in this model, the SSD is a lot more straightforward, whereas in the EBOF, we have to really worry about the Ethernet connectivity and the switching. We've been doing studies with partners in this space, and we're taking a really close look at the configurations and the value propositions. So in this view, we take our standard NVMe-based SSD, and we place it in a carrier, and then we are currently using a third-party Ethernet switch, and we bolt it together, and then we put 24 drives into a 2U server, and we ran a bunch of testing, and we're doing a bunch of workload testing, and we're really measuring the performance, the characteristics as compared to other models. And there's been a couple of key takeaways. As the cores in the compute complex increase and the number of threads in those cores increase, we have to optimize the storage subsystem for these cores. Now, ideally, we found that we'd attach about 512 gigabytes per VM per core, and we're looking at performance of about 250K IOPS per terabyte. Now, what makes this start to be really interesting is taking it one step further. We're looking at capabilities now injected directly into the SSDs to enable and help make this model more effective, whether it's a JBOF or an EBOF. Specifically, including things like physical functions to offload the hypervisor, ATS or address translation services to bypass the CPU IO MMU, and command memory buffers within the SSD. Bottom line is that in these configurations, we're adding more capability to the SSD, and that allows for more scalability upwards to faster speeds. And we want to take the workload off the CPU resource that's necessary to manage the storage pool. So we're moving more of the workload down into the storage subsystem, thereby freeing up the CPU and even the VMs for other tasks.
But you're not talking about computational storage here. You're talking about essentially offloading some of the tasks from the CPU.
That's correct. So this is different than computational storage. My view of computational storage would be a separate processing unit in the SSD, whereby you don't have to pass all the data in the SSD back up to the host, and you could do local processing, create some results, and then pass the metadata and the results back to the host, thereby saving a bunch of network traffic. This is a little bit different. It's more subtle. It's basically taking those extra bandwidth cycles off the CPU, the VM, just for simple management of storage pooling across the network. But so they are different. I want to take a moment and talk about the capacity storage tier that I mentioned earlier. When we look at traditional enterprise storage, the SSD penetration is about 28% right now. But in the cloud, we only have about 8% penetration. And so the question is, why is there such a big disparity between these two? First and foremost, it's obvious that there's still a significant price gap in terms of dollar per gigabyte. You know, if you go back 3, 4, 5 years ago, the price delta between a 7.2K hard drive and an SSD was 14x. Last year, that shrunk to 7x. Over the course of the next couple of years, utilizing QLC technology, we expect to see that gap narrow to about 3x. So the price delta between the two technologies is shrinking over time. Secondly, data centers can mitigate the limitations of hard drive performance by scaling and doing a lot of parallelism. But the data center loves homogeneous environments. They like everything to be the same. So they're not a big fan of a lot of tiers in the memory storage hierarchy. And it's actually quite a big barrier to add a new tier because you have to manage it and it becomes complex. And so the capacity tier that I showed earlier is not something that will naturally be adopted. Rather, it's when the pain of scaling becomes too high, will the tier actually be adopted? And we're getting to the point now where that pain threshold is coming and we're being forced to do something different. So let me talk about that for a moment. The challenge is twofold. The HDD performance is not scaling as capacities go up. So storage workloads care about throughput. The challenge is that HDDs are serial devices. It has one output at a time. Every time you make a bigger capacity hard drive, it's still the same speed, putting out essentially one head of performance data at a time. However, a big contrast is in SSDs, which are actually parallel devices. As capacities go up, we put more NAND on the device, and therefore we get more flash channels on the backside of that device, and we get to balance it. And so as we increase the interface speeds, such as a transition to PCIe Gen 5, we balance that host interface with more channels, more flash on the back end, which gives you very nice scaling over time. So let me use the example in the chart. A typical configuration, a 2-year rack shown here. In about 2018 timeframe, with a 25 gigabit Ethernet link, which is widely deployed within the rack, going from each compute node up to the top of the rack, you could have about 12 hard drives that would essentially saturate the link, and that would create a balanced system. However, in 2021, as we see more 100 gigabit Ethernet, or in some cases 40 gigabit Ethernet, to saturate the bus, it would take 48 drives, which is no longer fitting in that 2U platform. Now, the hard drive industry is responding, and they're coming out with dual actuator hard drives to double that performance. And so if you did that, you can shrink that down to 24 drives. However, you can saturate that link with 12 PCIe-based Gen 3 SSDs, and that would also create a balanced configuration. But now let's project forward. If you look over the next 3 years, as network speeds continue to climb up to ranges of 400 gigabit, it would take 96 dual actuator drives to saturate or balance that system. But because SSDs are scalable, and you're increasing the interface to PCIe Gen 5, this can actually be serviced with the same 12 SSDs. Okay. So fundamentally, cloud operators, they scale with parallelism. However, that doesn't necessarily work for small block operations. So when you have small block operations to access metadata and small blocks of data, it's all about IOPS per terabyte. Since HDDs are serial, it can handle about 80 random operations on a 4K workload. But an SSD is 1,000 times higher. As capacities get larger on hard drives, the IOPS per terabyte continues to drop. And ideally, the cloud providers would like to operate about 10 IOPS per terabyte with a minimum of 5 IOPS per terabyte. But we're starting to see a drop below that minimum threshold as hard drives approach 80 to 20 terabyte capacity points with a single actuator. So to solve this problem, the HDD vendors have introduced multi-actuator solutions, which becomes a new storage tier, because the dual actuator hard drives are actually more expensive and they actually come with a little bit smaller footprint. And so by definition, you're actually in the hard drive space creating a new storage tier. And this, in my opinion, or our opinion, is it's a short-term patch. It's not a long-term solution for that minimum performance threshold. Now, this tends to break the homogeneous solutions that we talked about. Once that happens, it opens up the opportunity to look at alternatives. As QLC pricing continues to come down the cost curves, the TCO model suggests that when we're within that 3x pricing on a dollar per gigabyte perspective, then it makes economical sense to shift this portion of the data center over to flash. Now, on our part, it's going to require some new innovations to drive the costs down, but we absolutely believe that there's an opportunity for this transition to occur within the next couple of years. Now, I would be remiss to kind of talk about industry standards from the perspective of form factor. This is a little bit near and dear to my heart because with all the form factors in the industry, we tend to have a very complicated skewing model. The predominant form factor, as we all know, is 2.5-inch form factor, which is the legacy hard drive form factor. And on the left side of this chart, you'd see in gray several almost proprietary solutions, adding cards, which were kind of kludgy. They weren't hot swappable, things like that. NGSFF and the ruler form factors come out to market. We are absolutely in a transition from that legacy hard drive form factor over to a NAND flash optimized form factor utilizing EDSFF form factor, or the enterprise data center SSD form factor. And these are form factors that are optimized for NAND flash. So for example, at the bottom of the chart, if you look at an E1L, which does look a lot like a ruler, we can get capacities of 64 terabyte into that form factor now, with a path to getting to 128 terabytes in a single form factor. And then you could take those and put those into a 1U server and get an extremely dense, high capacity JBOF or EBOF that has a very small footprint and meets the needs of very, very high capacities, especially with our QLC technology. Today, we're seeing systems come to market with E1S, and we expect that to transition to E3.S over time, along with the PCIe Gen 5 transition, which is coming in the next couple of years. In conclusion, as Raj mentioned earlier, the industry is drowning in data, but yet starving for knowledge. Our job at Micron is to enable customers to extract the maximum value from data. So this memory storage hierarchy is a continued investment on our part to address the needs of the industry, address the needs of our customers in a manner that gets them the fastest access to memory and storage in the most cost-efficient manner. We're doing it with driving standards, both, we talked about several things there, JEDEC, and we talked about form factors, innovating at every single level within this hierarchy, and addressing each one of these tiers with a complete portfolio that all kind of gets comprehended together and gets validated and qualified together as a complete portfolio.